Hey everyone, Houston Math Prep here. When we are trying to evaluate the limit of some sort of a rational sequence, we have something over something else, and as the term numbers get really large, we get some expression like 0 over 0, or some infinite value over another infinite value, whether it's positive or negative overall. These limits don't really tell us. These forms, the limit could actually be any real number. It could be infinity, it could be negative infinity. We just don't know by looking at these as we do some others. So these limits are actually called indeterminate forms, and the way we deal with indeterminate forms, if you recall from dealing with these in functions, what we've done before is we've had the limit of some function over another function. We've taken the derivative of those functions separately and then tried to evaluate the limit again that way, and that's called L'Hopital's rule. For sequences, all we really want to do to make an adjustment here is, as long as we can think of both of these sequences as some sort of function of n, basically you have a function that mirrors the behavior of A and a function that mirrors the behavior of B, then we can go ahead and apply the same rule, L'Hopital's rule, for the limit of some sequence over another sequence, taking the derivative as though they were functions. Remember, these aren't functions, they're only just defined for whole number values of n. Taking a look at a first example here, we have the limit of e to the 1 over n minus 1 all over 1 over n. So if we try to evaluate this by imagining what we would get, if I plug in a larger and larger value for n here, this 1 over n is going to approach 0. So this will approach e to the 0 minus 1, and then on the bottom, 1 over n, we're going to have another 0. So if you look at this e to the 0 minus 1, that's going to be 1 minus 1. We get 0 over 0, and so this is indeed an indeterminate form. And 0 over 0 means we can apply L'Hopital's rule. So I'll go ahead and just write LH so that you know that I'm applying L'Hopital's rule. So if you look at the limit here, so that will be equal to the limit of, we'll need to take the derivative of the top and the bottom separately. So the derivative of the top, e to the 1 over n, assuming this was just a function of n, then I would get itself, so e to the 1 over n, and then times the derivative of the inside from the chain rule. The derivative of 1 over n is going to be negative 1 over n squared. Okay, 1 over n is like n to the minus 1, so you can do power rule there if that's confusing at all. Minus 1, that's just a constant, so that would drop off if we do a derivative. And then the bottom is 1 over n, and that's the same as this exponent here, so we're just going to simply get what we got from the chain rule above, negative 1 over n squared. So you can, I think, see that we're going to get some reducing here, so we'll just get the limit of e to the 1 over n. If we now try to plug in a larger and larger number for n, then this is again going to go toward 0, so we will actually approach e to the 0, and in this case our limit is 1 for this sequence. Here's another one, the limit of the natural log of n over the square root of n. So if we think about plugging in larger and larger values for n, the natural log function, if you think about the graph of y equals ln x, goes up to the right forever. So we are going to get an infinite value on the first one. For this one here, square root of n, as we take square root of bigger and bigger numbers, millions and billions, this also blows up infinitely large. So we do have an indeterminate form here. This one is actually the infinite over infinite form instead of 0 over 0. We'll go ahead and apply L'Hopital's rule here. And so this limit will be the same as if we take the derivatives of each of these as though they were functions of n. So the derivative of ln of n is going to be 1 over n. And then derivative of square root n, think of this as n to the 1/2, we'll get power coming out 1/2, and then we'll get the power going down by 1, so that would be n to the negative 1/2. Okay, so we'll go ahead and clean this up a bit. I have 2 here. 1/2 on the bottom would actually be a 2 out front. And then I might do a few different things, I guess, to simplify this. I'm going to go ahead and multiply the top and bottom by n. And maybe that'll help us decide what's going on here. So on the top then, I'm just going to get n times 1 over n would just be 1. And then the bottom here, n to the negative 1/2 times another n. This is like n to the 1, so I would add these exponents, that would be n to the 1/2. So what we're really looking at then is the limit of 2 over the square root of n. And we know that the square root of n blows up infinitely large. So this limit, we have a constant over something that gets really, really big. That limit is in fact going to be 0. Okay, so you can see in the previous one we got 1, in this one we got 0. We could get any real number, we could get infinity, negative infinity. That's what an indeterminate form is when we have one of these 0 over zeros or infinity over infinities. Let's look at some more indeterminate forms. So here we have a form 0 times some infinite value, whether it's positive or negative infinite value. The problem with this is that it's not set up to be solved by using L'Hopital's rule. L'Hopital's rule applies to fractions that are 0 over 0 and an infinite value over another infinite value. So here we need to rearrange this form so that it is set up for us to use L'Hopital's rule. Our hint here is going to be for you to just take this product and simply write it as a quotient. We'll look at an example of what we mean here. So if we have the limit of 1 over n times ln of n. So if I just think about plugging in bigger and bigger values, then this first part, 1 over n, would go to 0. And the limit of the natural log function is an infinite value. So I get 0 times infinity. And that's obviously an indeterminate form, as we can see here. So I'll write that indeterminate form. It's always good to be clear about what we're doing. The idea is then to write this as some sort of a quotient, as a fraction. The easy way to do this is really just to put the ln of n on top of the fraction, and it stays the same thing, right? So this is really just the same as thinking of this as the limit of ln of n over n. And now it's a fraction. You can see that if we try to evaluate this, we are again going to get an indeterminate form, right? If you're not sure, you can always check. If we plug in bigger and bigger values for n, the top is going to become larger and larger, the bottom as well. So it's still, again, an indeterminate form. But now that it's in fraction form, infinity over infinity, we can now apply L'Hopital's rule. So if we apply L'Hopital's rule, then that will equal the limit of the derivative of each one separately. The derivative of ln of n is 1 over n, and the derivative of n is just going to be 1. So we can think of this as the limit then of just 1 over n. And again, obviously, as we plug in larger values of n, this limit is going to be 0 for this one. Looking at another one, we have the limit of n times e to the negative n. If we try to think about what's happening here for the n part, obviously that's going to get infinitely large as we plug in bigger and bigger things for n. As the term numbers get big here, e to the negative n, we'd get e to some really, really negative value. If you're not sure, you could think of this part as 1 over e to the n. So as we get larger and larger values of n, the denominator is getting really large. So we get 0 for this one. So this is 0 times infinity. This is indeterminate form as well. And so making this into a fraction, maybe we think of the e to the negative n just in this way, 1 over e to the n. So that's going to be the same as thinking of this as limit of n over e to the n. You can think about plugging in still. Now we look at this. This is infinite over infinite if we try to get larger and larger values of n in there forever. So still in a indeterminate form, but now I can use L'Hopital's rule because the form is correct. So we'll apply L'Hopital's rule here. That will give us the same as the limit of the derivative of each. So the derivative of n is 1 on top. The derivative of e to the n on the bottom is still e to the n. So that makes it nice. We have a 1 on top now. So we get 1 on the top. We get something very, very large on the bottom, 1 over something getting infinitely large on the bottom. Our limit here is going to be 0 for this one. An additional form that we see occasionally is some infinite value minus another infinite value. The issue is that both of these terms may approach infinity at different rates. And so the question is then, what is this infinity minus this infinity? It's not really clear just knowing that both things become infinite. You can just simplify what you have, or you can maybe write it all as one fraction. That's what I'm going to do here. I'm going to write it all as one quotient. If you look at what I have here, I have a limit of this rational expression minus 2n. If you just look at the first part here, you'll notice that I have a stronger term, the n square over the n, right? So if I look at this, this is indeterminate by itself, but we know that a higher power on top over a smaller power on the bottom, this is going to get infinitely large. And if I plug in larger and larger values here, this is also going to be infinite. So this is going to give us an infinite amount minus another infinite amount. This is an indeterminate form, but we'll need it in the 0 over 0 form or the infinity over infinity form to deal with this with L'Hopital's rule. So what I'm just going to do is I'm going to think of this over 1, and I'm simply going to get a common denominator and put these together. So I will go ahead and just multiply this piece by n plus 3 on the top and the bottom. So we're going to keep the 2n squared minus 5n over n plus 3. And over here, we are going to take 2n times n plus 3, and that's going to be over n plus 3 now. And so we'll do some combining here, right? So I'll have my limit. Then on top, I will have 2n squared minus 5n. Think about distributing the negative 2n. So I'd have minus 2n squared, that's convenient, minus 2n times 3, so that'd be negative 6n there. And then everything is going to be over n plus 3. And if we see some things reduce here, we have 2n squared minus 2n squared. That will be 0, right? So we end up with the limit of negative 11n over n plus 3. So in this instance, you can either compare lead coefficients, or you can say, well, this is infinity over infinity. And this is an indeterminate form here, so let's apply L'Hopital's rule. So if we apply L'Hopital's rule, then that's just going to be the limit of negative 11 on the top, and the derivative of the bottom would be 1, right? So our limit here is negative 11 for this one. Our last three indeterminate forms are all exponential forms. We have 1 to the infinity, we have infinity to the 0, and we have 0 to the 0. For each of these forms, we'll use logarithm properties. So what we'll do is, to deal with the exponent, we'll let y equal our limit that we are trying to find. And we will take the ln of both sides. So we'll take the natural log of both sides. We can do that. No problem. ln is a nice continuous one-to-one function on the positive values there. And then we'll go ahead and use properties of logs to get our exponent outside of the log and deal with it as a product that way. So let's go ahead and look at the limit of 1 plus 1 over n all to the n. This is a pretty commonly used limit here. So the first thing we'll do is we'll let y equal the thing we're trying to find, right? So y is equal to the answer that we want from this problem here. So what we'll do is we'll now take the natural log of both sides. So I'll say ln of y equals the limit of ln of 1 plus 1 over n to the n. Okay. At this point, now that we have a log, I can go ahead and use properties of logs to move the exponent out front. So ln of y is going to equal the limit of n times ln of this stuff in parentheses here, 1 plus 1 over n. And then if we try to evaluate this limit, you'll notice that this is going to be something infinite. This would become 0, so we'd get 1 plus 0, and the ln of 1 is 0. So I get infinity times 0. This is an indeterminate form here. So what you'll notice with this product, when we had 0 times infinity, we just wrote this as a quotient. So what we'll do is actually make the reciprocal of one of these and put it in a denominator. This n looks simpler than this, so I'm going to go ahead and make the reciprocal of this. So this is kind of the opposite of what you normally think of when dealing with fractions. Normally, when you have a fraction in a fraction, we bump that up and multiply by the reciprocal. Instead, what we're doing here is actually the opposite of that process. We are taking something out front, bumping it down, and dividing by its reciprocal. So this is a similar statement, but because we want to use L'Hopital's rule, we need it in fraction form. Okay, so if we go ahead and look at this, we have, again, ln of 1 as n gets really large, which is going to be 0. And 1 over n would approach 0 as well. So this is an indeterminate form. So we'll say L'Hopital's rule so that everybody knows what we're doing. And then we'll say ln of y is equal to the limit of, now what is the derivative of ln of this? Well, derivative of ln something is 1 over that something, so it's 1 over 1 plus 1 over n. Chain rule though, times the derivative of what's inside. The derivative of the 1 is 0. Derivative of 1 over n is negative 1 over n squared. And then a similar thing happens on the bottom. We have derivative of 1 over n, we get negative 1 over n squared. And so we get some reducing there. And so that will tell us then that ln of y is equal to the limit of 1 over 1 plus 1 over n. And as n gets really large, this fraction is going to become 0. So we will get 1 over 1 plus 0, 1 over 1, which would be 1. So that tells us then that ln of y is equal to 1, which is not quite our limit yet, right? We said that y was going to be the answer to our problem. So how do I solve for y? I'll need to get rid of the natural log. So what I'll do is I'll take the exponential base e of both sides, and that then tells us that y is equal to e. And so our limit for this one is actually the number e. Looking at another example here, limit of n to the 1 over n. If we think about what would happen, n is going to get really large, so we'll get a base that gets infinitely large. And then this 1 over n will get something that approaches 0. So we approach an infinite amount on the bottom, we approach 0 on the top. This is an indeterminate form. We will do a similar process where we use logarithms. We'll let y equal our limit first. So y equals the limit of n to the 1 over n. We'll then take the natural log of both sides to deal with that exponent and rearrange this. So that will be the limit of ln n to the 1 over n. So we go ahead and bump that out with properties of logs. And we'll say that's going to be the same as the limit of 1 over n times ln of n. And this should look similar to something that we already did in this video. Remember when we plugged this in, we got 0 times some infinite value when we did 1 over n times ln n. So this is an indeterminate form again, and we would deal with this the way that we did last time. We will simply make this product into a quotient, and we'll solve that way. So we'll get ln of y equals limit of ln of n over n. We'll still get an indeterminate form, infinite over infinite. We'll apply L'Hopital's rule now, though, because it's in the form where we can use L'Hopital's rule. And so we'll get that ln of y is equal to the limit of 1 over n over 1. Just sort of redoing what we did before, so that will be the limit of 1 over n, and so that will tell us that ln of y is equal to the limit of 1 over n, which is 0. Get rid of the ln because it's actually y that we want for our answer, because we let y equal our original problem. We get y is equal e to the 0. That tells us that y is equal to 1, so my limit for this problem is 1. All right, our last form, indeterminate form, 0 to the 0. Here we have a limit of 4 over n to the 1 over n. So think about 4 over n is getting smaller and smaller as n gets large, and 1 over n is also getting smaller and smaller as n gets large. So this is indeterminate form 0 to the 0. And we'll do a similar process. We let y equal our limit. Y equals the limit of 4 over n all to the 1 over n. And then we go ahead and use natural log. So ln of y equals the limit of ln 4 over n, the 1 over n. And we'll use properties of logs. We'll now move all that out. So ln of y is equal to the limit of 1 over n times ln of 4 over n. You can see that this is indeterminate again. We get a limit of 0 there. This one may be just a little bit trickier to see. So the inside is 4 over n, which approaches 0. And as we approach 0 on the graph of the natural log function from the positive direction, then this goes towards negative infinity. So we get 0 times an infinite value there. This is still an indeterminate form. And remember to use L'Hopital's rule. We will need to write this as a quotient. So we'll go ahead and rewrite this then. ln of y equals, the easiest way to make this a quotient, I think, is just to write ln of 4 over n and write that all over n, and that's the same as what we had here, right? If we look at what happens now with this, we have ln of something that approaches 0 from the positive side, so we will get a negative infinite value here. Down here, this is going to blow up infinitely large, so we get an infinite value over an infinite value. So this is still an indeterminate form. And we can now apply L'Hopital's rule because it's in the infinite over infinite form that we need to use that. So we'll say ln of y is equal to the limit of, taking the derivative here, would be 1 over 4 over n, also known as n over 4. And then the derivative of what's inside is going to be negative 4 over n squared. The derivative of the bottom, I think everybody would agree, is just 1. Okay, if we go ahead and simplify now, obviously the 4's will reduce to 1. This n will reduce with 1 of the copies of n squared there, so we'll get ln of y is equal to the limit of, we'll get negative 1 over n once we reduce all of that. And then the limit of negative 1 over n is going to be 0, because this is getting really large on the bottom. So that then tells us that ln of y is equal to 0. And then if I get rid of my natural log by taking the exponential of both sides, we get that y equals e to the 0. So in this case, y is equal to 1, and that is our limit that we were originally looking for. All right, so that's how to deal with all 7 of your indeterminate forms when you are finding limits of sequences. Thanks for watching, everyone. We'll see you in the next video.